partial fractions decomposition. Years ago in school, you used to add fractions, just numbers, fractions together. And the goal there was to be able to, you recall, find the least common denominator. And then as years progressed, you looked at algebraic expressions. They were called rational expressions, basically fractions that had variables in them, a, b, x, y, whatever. And then the same thing was asked of you to be able to add, subtract those fractions, those rational expressions. Again, the same technique was applied. Be able to determine the least common denominator. Once you have the same denominators, you add those fractions, and you get one fraction at the end. Does everybody remember that? Does everybody remember that? Does everybody remember that, right? So, today, what we talk about with partial fractions is actually called partial fractions decomposition. And what that means is, what if I'm given one fraction, can I decompose it back into its parts? So all we're going to talk about today is going the other way. Years ago, you had 2 or 3 fractions you want to add to get one fraction. What if now we give you that one fraction and then we say, break it down into the parts to get those separate fractions? That's all we're doing. Right? So what you will learn to decompose here, this P over Q is a fraction where Q has only distinct, that means different linear factors. When you factor your denominator, if you can, if those factors are different, then there's a separate technique for partial fractions. If those factors, those linear factors in your denominator, once you factor, if they are repeating, then we use a different technique. And then the third idea is that if you have a fraction, you want to decompose it, and if your denominator, that's Q, here, if it has non-repeated prime quadratic factors, I didn't give you any of these for the homework nor for the quiz, and likewise didn't give you anything there for item number 4. I did put the explanations here in the lecture, but 1 and 2 I think would be enough. If we can get those, hey, I'm happy. So again, the idea behind partial fraction decomposition is, you see these 2 fractions that we start with. The first is 3 over x minus 4. That's one fraction. Then the other is 2 over x plus 2. So it's 3 over x minus 4 minus 2 over x plus 2. And then we want to try to combine them. You recall that we did that by finding the LCD, least common denominator, which would be x minus 4 times x plus 2. And then once we rewrite those fractions with the new common denominator, then we can, in that sense, combine the numerators all over the common denominator, and you get your result. So the goal here now is, if we're given this guy, can we work in a process of successful steps to get these 2 fractions? That's our goal. So we call that partial fraction decomposition. You want to break down this fraction, decompose it into its parts. So here are the steps. So, and I got this right from the book, Steps in Partial Fraction Decomposition. Set up the partial fraction decomposition with the unknown constants. I call them generic terms, A, B, and C. And I'll show you how to string those up in just a moment. And then from there, multiply both sides of the resulting equation by that least common denominator, which will already be your denominator on the left side. So there's no figuring out here what the LCD is. simplify the right side of the equation. Number 4, write both sides in descending powers, equate coefficients of like powers of x, and equate constant terms. Solve the resulting linear system for A, B, C, etc. Sounds like a lot of mumbo jumbo. So I think probably best is to, as we take a problem, show you the steps as we go along. Well, 2 things here. The first is, if I have a partial fraction of P over Q, where Q has different roots or linear factors, what are they talking about? These guys are different. So if they're different, then I'm going to write, here we call this A sub 1, this A sub 2, and so on. We're just going to call them A, B, and C. I call those just generic terms. Those generic terms we want to determine. So that'll be our goal. And notice that each generic term is written over one of these linear factors. That's how we're going to do that. And we do that if these linear factors, that means what's in my denominator, if they are different factors, right? If they are repeated, we're only going to have 2 cases, that this previous page here, and then types that look like this. If we have repeated roots, what does that mean? You're going to have something like, say for example, you have 5 over x minus 3 to the 3rd power. So that means that x minus 3, and maybe I write that to the 4th power. This x minus 3 is repeated 4 times. So that's what we mean by a repeated factor or repeated roots. The way we do that is a little bit different. Notice how if we have repeated linear factors, the linear factors are the ones downstairs, then we're going to count up starting with the first one from the 1st power, 2nd power, 3rd power, all the way to the nth power. So for this, if we break this down, this would be A over x minus 3 plus B over x minus 3 to the 2nd plus C over x minus 3 to the 3rd, all the way up till we get to the 4th power, plus D over x minus 3 to the 4th. Now the challenge for that example is we must determine A, B, C, and D. That'll be our goal. And then once you find A, B, C, and D, then you just put those back in and just write those numbers, whatever A is over x minus 3, plus whatever B is over x minus 3 to the 2nd, plus whatever C is over x minus 3 to the 3rd, and so on. Now, we're not going to deal with that case, nor with that 4th case. So I think what's best is let's just take a problem, and as we look at this problem, we can talk about the steps. And I apply the steps, the same steps, each time as we go, okay? So here's what we're going to do. A couple of things. I want to determine, look at my denominator. When I factor my denominator, are the factors different or are they the same? That's the first. So if they're different, we call those distinct roots. Okay. So notice that x plus 4 and x plus 9 are different, right? So I'm going to write this as, if they're different factors, this is going to be A over x plus 4 plus B over the other guy, x plus 9. Okay. So that's the first step. The second step is we're going to multiply everything by the least common denominator. Step number 2. Multiply both sides by the LCD, which is the denominator on the left side. It's already set up for you, right? So for that step, we're going to say x plus 4 times x plus 9. This is times this left side, 5x plus 30, all over x plus 4 times x plus 9, equal to here x plus 4 times x plus 9 times this a over x plus 4 plus the LCD x plus 4 times x plus 9 times b over x plus 9. All right. Now, the reason that we're multiplying by the LCD is that we want to clear the fraction. We want to get rid of the fraction. That's the goal. So now look at what cancels out. X plus 4 is divided by x plus 4. X plus 9 is divided by x plus 9. Here, this is only x plus 4 that's canceling. Over here, x plus 9 is canceling with x plus 9. Does that make sense? Okay. Now let's just rewrite what we have left. So what I have left on the left side is 5x plus 30 is equal to a times x plus 9 plus b times x plus 4. Now, when the factors are distinct, excuse me, when we have distinct factors, all we do here, and it's easy, is you see on the right side where you have an x plus 9 and you have x plus 4. So I have two of them. So first what I'm going to do is let x equal, what makes this term go out to be 0 if x is equal to negative 9. So I'm going to first let x equal to negative 9. Plug in it, wherever I have x, I'm going to plug in negative 9. When I do that, I'm going to be solving for b. Do that. Secondly, let x equal to negative 4. That'll cancel out for b, and then I can solve for a. So secondly, let x equal to negative 4, plug in negative 4 wherever you have x, and then just solve for this other variable. It'll be automatic. Okay? Now that works out when the factors are distinct. That is when my denominators have different terms. Different terms in the denominator. So let x equal to here the number that cancels one variable in order to solve for the other. Now that's nice and smooth and sweet for distinct factors. It works here automatically. So this is step number 3. So let x equal to negative 9. Because if I let x equal to negative 9, that's going to cancel out a, and then I'm going to be solving for b. All right? So this implies that I have 5 times negative 9. Wherever you have x, you're going to plug in negative 9 is equal to a times parentheses negative 9 plus 9 plus b times negative 9 plus 4. All right, that left side is negative 45 plus 30, so this is negative 15. That's equal to, the a goes out because that's a times 0, right? So this is equal to, here, negative 9 plus 4 is negative 5 times b. So I can solve for b. So b is equal to 3. Okay. Now we do the same thing. Here's what I'm looking at. I'm looking here. I'm looking there. So for this one, let x equal to -9. It's just the opposite. It's going to cancel out that. And then for this one, you let x equal to -4. So we do that now. Crazy phone. Do you have a phone that just talks by itself? Yeah. Do you have a phone? It's crazy. I just got it this past summer, and it's driving me bonkers. So we did that. So now we're going to say let x equal to -4. So, and I'm looking at this equation here. So I have 5 times -4 plus 30 is equal to a times -4 plus 9. And then this is plus b times -4 plus 4. All right, so I get -20 plus 30, so that's just 10, and that's equal to, what is that, 5a? And so I get a is equal to 2. So a is equal to 2, so this becomes 2 over x plus 4, right? And plus, now if b was negative, I would say negative here, but since b is positive, this is just plus 3 over x plus 9. So we've just decomposed that fraction. Okay. All right. Does that make sense? Let's keep digging. Okay. As Clint Eastwood told Levi Elliott in The Good, the Bad, the Ugly, there's two kind of people in the world, my friends. Ones with loaded guns and the others who dig. Well, Clint Eastwood had the gun, obviously, so he told the other guy, you dig. So let's keep on digging, right? So all right. Write the partial fraction in decomposition. Write the partial fraction decomposition of the following rational expression. Look at our denominator. I have 3 terms there. One is x, the other is x plus 4, the other is x plus 5. Are they all different? Please say yes. Okay, yes, they are. Okay. You know, let me say this, and I don't have too much time because I got to cover these 2 sections, but I don't know about you all, but I know when I was in school, I never liked the teachers when they would like ask all these questions and they want you to say what's in their mind, you know, and they're giving a sentence or a paragraph and they stop and say, "In what class?" And I'm like, I don't know. You know, I'm like, dang, you know, I'm dumb. Leave me alone. You know, and I mean, I get the stuff, but it's like I don't think the way they think. You know, just let me after class. I go back and reprocess all this stuff, and I get it. But so I've always made sure that I wouldn't, you know, put people on the spot and say what class and what. Wow, no. Boy, I mean, some people can get it. Some people are sharp like that. Bless their hearts. So they're all different. So since they're different, we're going to say A over the first term plus B over the next term plus C over that last term. We do that when they're different roots. Now again, if they're repeated, then it's going to be a little bit different, and we'll show you that in just a minute. Multiply both sides by the LCD. Now, I hope it's okay, but I want to go ahead and just do my shortcut and just go right to it. Because in this previous one, I did a whole lot of writing there. A whole lot of, you know. So if you kind of see what's going on, if you can run with me, I don't want to mess anybody up, but it's just the way that I do it, and I just get right to it. Here's the thing. On the left side, this denominator here, that's already the LCD. If I multiply the left side by the LCD, well, that denominator is already gone. So all I can write for the left side is just that numerator, 6x squared plus 4x plus 20. I just write that. All right? So I'm multiplying both sides by the LCD. So I get 6x squared plus 4x plus 20 is equal to, now, when I multiply the LCD times each of these fractions on that right side, it's going to kill that term, that only term that's in the denominator. It's going to leave the other two terms. Are you with me? For each fraction. So for this a over x, it's going to kill the x. All I have left is a times x plus 4 times x plus 5. Does that make sense? You see that? Again, we're multiplying each term by the LCD plus b. Now, once I multiply the LCD times b over x plus 4, it's going to kill the x plus 4 in my LCD. All I have left there is x times x plus 5. Plus c, you get it, I'm killing the x plus 5 from my LCD, so all I have left is c times x plus 4. Does that make sense? So instead of, having to write all this stuff all out, I think we kind of get it, right? I'm multiplying everything by the LCD. So I just say it here. And that gives us that next line. Okay? So good. So here's what I'm going to do. I'm going to start here with the x plus 4. I'm going to let x equal to negative 4. Right? So that implies wherever I have x, I'm going to replace the x with negative 4. Now check this out. Wherever x is negative 4 on the right side, wherever x is negative 4 on the right side, it's going to be a 0. So I'm not going to have it. I'm not going to have this a term. I'm not going to have that c term anymore if I let x equal negative 4. So all I have left is this right here. Critical thinking. b times negative 4 times negative 4 plus 5. Is that okay? You can put that negative 4 in each term, but automatically, if I got x plus 4, and then I'm letting x equal to negative 4, that's going to be negative 4 plus 4, that's 0. So that expression there goes out. 0 times anything is 0, right? So here, this is 6 times 16 minus 16 plus 20. And that's equal to, this is negative 4 plus 5, that's 1. This is just negative 4b. So 6 times 16, that's 96. And then that's plus 4. So this is 100 is equal to negative 4b. So divide both sides by the negative 4, this implies that b is equal to negative 25. Okay. I do the same thing here for x. Look, x is equal to 0, and then after that, we let x equal to negative 5. Let x equal to 0. So I have 6 times 0 to be squared plus 4 times 0 plus 20 is equal to, now the terms that have just the x by themselves, that's going to be a 0 automatically. So I get 0 for the b term and the c term. Put a 0 there, that goes out. Put a 0 here for c times 0, that goes out. All I have left is over here. So I'm going to focus on a. So this is a times 4 times 5. They're letting x equal to 0. So this gives us Here 20 is equal to 20a, so a is equal to 1. Is everybody with me? Now I have one more. I have that's x plus 5, so let x equal to negative 5. Let x equal to negative 5. So start with the left side, plug in x to be negative 5. 6 times negative 5 squared plus 4 times negative 5 plus 20. Now, for the terms for x plus 5, if I put in a negative 5, it's going to be 0. So a and b go out. So all I have left focus is on that c. So this is c times negative 5 plus 4. So I get 6 times 25, and then this is minus 20 plus 20. That cancels out. That's equal to, this is negative 1 times negative 5, so that's just 5c. So what is that, 150 is equal to 5c, and so c is equal to 30. So now we can put everything together, and I want to put it right here just to say equal. Just going to replace a, b, and c with what we found. So a is 1, so this is 1 over x. B is negative 25, put the negative there, 25 over x plus 4. And then c is plus 30 all over x plus 5. Put the answer down there just to check, just to make sure we're all on the same page. Any questions there? Let's see if we got one where we have repeated root. This is not repeated, but let me just string this out, and then I'll go to one where we do have repeated linear factors, and then move on to the next section. So if we write this out, this is 5x squared. Just that numerator just stays the same, minus 5x minus 4. You got to factor this denominator. You factor x to the third minus x. First, you can pull out an x, so you get x times parentheses x squared minus 1. And then when you factor x squared minus 1, you remember that's just x minus 1 times x plus 1, right? So my factors here is x minus 1, x plus 1. Now they're all different roots, different factors, so we follow the previous steps that we just got through doing for those last two problems. So this would be, and I just set it up like this, a over x, and you can finish it plus b over x minus 1 plus c over x plus 1. And then everything else would follow, okay? The only difference with that problem is that denominator, you had to do some factoring, right? Had to factor that x cubed minus x. So we don't throw away factoring. All right. Here's the one with the repeated root downstairs. That x minus 6 is being repeated 3 times. So if you have repeated roots, here's how you write it out. This is a over x minus 6 plus b over x minus 6 to be squared plus c over x minus 6 to the third. Okay? Now I'm going to scroll back to show you where that came from. Here, partial fraction decomposition of a rational expression where q has repeated linear factors. That's this guy right here, right? See the example. Okay. So that's what we're using. So we're going to multiply both sides by the least common denominator, which is x minus 6 to the third. I'm going to go ahead and just put all that in there so you can kind of see what's going on, because this is a little bit different than the ones from before. Multiplying each term by the LCD. All right. So we do that to clear the fraction, right? So here, that's going to cancel. Now, automatically, over here for this C part, that guy is going to cancel there because they're the same. And then we do some simplification for the rest. So, the left side is x squared minus 7x plus 5, that's equal to a. Now notice that when I divide x minus 6 to the third divided by x minus 6, just one of those cancels out, right? So all I have left is in parentheses x minus 6 to the second plus b, x minus 6 to the third divided by x minus 6 to the second just leaves me with 1 x minus 6. Now, my pastor, when I was a child, Pastor Nathaniel Castor, he would always say, "Isn't that right?" Well, he was an old, big old fat dude from Mobile. He would tell you, "I'm from Mobile County. I come all the way up here to preach the gospel." He would drive like 90 miles from Mobile up to Orville by Selma. And our church, back then, we met like once a month, country churches, once a month, twice a month. I come all the way up from Mobile County. Didn't he rise? Isn't that right? Big old jaws. Man, I loved him. He was a sweet guy. Yeah. Okay. So notice, see, we have a problem with this one. I only have one term, x minus 6, right? But I have two of these generic terms, a and b. So I'm going to go ahead and let x equal to 6. Let's see what we get, when we do that. Oh, I'm not finished. This is plus. Forgot the plus c. Okay. So we let x equal to 6. So we have 6, the left side, 6 squared minus 7 times 6 plus 5 is equal to, I'm just going to plug in, since I'm plugging in everything, this is 6 minus 6 to be squared. It's going to go out anyway, plus b times 6 minus 6. That's going to go out, plus c. So here I have 36 minus 42 plus 5. That's equal to c, right? And so here I get 41 minus 42, so I get negative 1 is equal to c. Now, based on that method, that's all I can get, because I don't have anything else to say let x equal to. You see that? You see the problem? Right? Before we had different factors. So I can let x, if it's like x times x plus 5 times x plus 4, I can say let x equal to 0 for one case. Let x equal to negative 5, right? For the second case, let x equal to negative 4. But I don't have all those. I only have x minus 6. So all I could do there was just say let x equal to 6. So that brings us to the method of just writing out the entire equation. What equation? This line right here. We have to write everything out and equate corresponding parts together. That's what we're going to do. If I have x squared over here and an x squared on the right side and left side, then whatever their coefficients, I set them equal. If I have x by itself on the left side, x by itself on the right side, give me a t, give me a z. No, okay. If I have x by itself on the left side, x by itself on the right side, the coefficients, whatever is multiplied to, I set those equal. Corresponding parts of an equation are set to be equivalent. So, let's see. This is step number 2. This is for, here we have, please note, repeated roots. Oh yeah, repeated roots. So we have to set corresponding coefficients equal. So this is star. All right, so we take star, simplify it. Simplify star. So the left side is already simplified. X squared minus 7x plus 5 is equal to, this is a times, FOIL that out. This is x squared minus 12x plus 36 plus bx minus 6b, bless you, plus c. Keep on simplifying. Keep on trucking, baby. So this is a times x squared minus, I'm going somewhere, so hold on. Stick close to me. 12ax, just running this a through the parentheses, plus 36a plus bx minus 6b plus c. All right. So now I'm going to see if I can write that right side to make it look like the left side. The left side is something x squared plus something x, then plus a constant. So I'm gonna now group here in descending order the right side. So rewrite the left side, x squared minus 7x plus 5, plus, I'm going to get the x squares together. I only have one x squared, it's just a x squared. Now I'm going to get, going down to x, I'm going to get the x's together, plus x, put that in parentheses, I have minus 12a, plus I have a b times x. So this is all times x. Everything left I have are just coefficients. 36a minus 6b plus c. So this statement up here for the note, repeated roots set corresponding coefficients equal, that implies that we have this. Here's what I'm doing. This coefficient is 1. So I'm going to set the coefficient for x squared equal to the coefficient for x squared over there. I'm going to then set the coefficient for x, which is negative 7, equal to the coefficient of x over here, which is minus 12a plus b. And then the constant, which is c, pretty color, green. I'm going to set here the 5 equal to the constants over there. Corresponding terms set to be equal. So when I do that, this implies that 1 is equal to a, see, because it's x squared, right? So 1 is equal to a. Well, that's already solved for us. That's good. So we got a, we got c, so all we have left is to solve for b. But let's just keep going with the that bluish aqua color. That's negative 7 is equal to negative 12a plus b. I can use that to solve for b. And then that other one, at the end, we have 5 5 is equal to, this is negative 7, is equal to minus 12a plus b. And 5 is equal to 36a minus 6b plus c. Okay. Did y'all do this in high school? I did this, this is high school. Matter of fact, this entire class, and I was in a poor county. I was in Dallas County, and they didn't teach calculus. We wasn't able to have a calculus teacher, but man, they taught algebra like crap. I mean, they made sure you knew. I mean, I'd wake up, man, I'd have nightmares getting strangled by algebra. Ah, what's wrong? My brother's like, what? He said, what? Algebra. Anyway, but okay. So sometimes you don't have to use all this stuff. Just get what you need. Now, what we need is B, because we got C, right? And we got A. I just need B. So I'm going to just use the second part. Negative 7 is equal to negative 12a plus b. I don't care about the 5 equal to 36a minus 6b plus c. That's my Kevin Hart impersonation. I don't know if you could pick anyway. So anyway, so let's take negative 7 is equal to negative 12. We know what A is. And we know this place. A is 1 plus B. Right? So we add 12 on both sides. So we get 12 minus 7. We get 5 is equal to B. Okay? I mean, we got it. So then we write the answer. We go back and replace the A. Since my space is out, well, I just put it here. So the A is 1 over x minus 6 plus B plus 5 over x minus 6 to the second. See, when you write the answer, this is really the answer here, just missing those generic terms A, B, and C. So you write your answer, just go back and replace A, B, and C. And then plus C, that's a minus 1 over x minus 6 to the third. And I put the answer up there just to make sure that I'm doing it right. All right. So I'm going to stop with this section because I think I've kind of, whipped this dead horse enough. So let me introduce the next section, which the next section is not as, I don't think is as intense as this guy right here. But this guy is pretty good mechanically, because mechanically you just following the steps, and it's going to work out automatically. Pretty cool stuff. All right.